Every single year, more than 2 billion tulip bulbs leave the Netherlands destined for gardens, parks, and flower markets across 100 countries worldwide. In a single day during peak season, Dutch flower auctions process over 40 million individual stems, moving through automated systems at speeds that would make your head spin. How do Dutch growers transform thousands of acres of greenhouses into precision flower factories that operate like clockwork? What role do robots play in planting, monitoring, and harvesting millions of tulips without ever bruising a single petal? And why does this tiny European nation control nearly 90% of the global flower bulb trade, while pioneering agricultural technologies that American farmers are now studying and adapting? Welcome to AgriCraft, where we explore the cutting-edge innovations transforming agriculture around the world and right here at home. Today, we are taking you inside the remarkable world of Dutch tulip cultivation, revealing the sophisticated climate control systems, robotic automation, and data-driven growing techniques that make the Netherlands the undisputed leader in commercial flower production. From bulb breeding programs that take 15 years to develop a single new variety, through computer-controlled greenhouses, where every drop of water is measured, to high-speed sorting facilities that grade flowers faster than the human eye can follow, we will show you how this industry combines centuries of horticultural tradition with 21st century technology. All will be revealed in this video. The tulip's journey to becoming a Dutch icon is one of history's most fascinating agricultural stories. These flowers are not native to the Netherlands at all. Tulips originated in the mountainous regions of Central Asia, growing wild across what is now Kazakhstan, Kyrgyzstan, and neighboring countries. Turkish cultivators brought tulips into intensive cultivation during the Ottoman Empire, and the flower became deeply embedded in Turkish art and culture. The very name tulip derives from the Turkish word for turban, reflecting the flower's distinctive shape. Tulips arrived in Western Europe during the mid-1500s, when a Flemish diplomat named Ogier Ghislain de Busbecq sent bulbs from Constantinople to Vienna. From there, the renowned botanist Carolus Clusius brought tulips to Leiden in the Netherlands in 1593, planting them in the botanical gardens where he served as director. Dutch merchants and growers immediately recognized the flower's commercial potential, and within a few decades, tulip cultivation exploded into a full-fledged industry and cultural phenomenon. The famous tulip mania of 1636 and 1637 represents one of history's first recorded speculative bubbles. At the height of the frenzy, rare tulip bulbs sold for prices equivalent to 10 times the annual income of a skilled craftsman. A single bulb of the Semper Augustus variety reportedly traded for an amount that could have purchased a Grand Canal house in Amsterdam. While the bubble eventually burst, the episode cemented the tulip's place in Dutch identity and established the foundations of a flower industry that would eventually dominate global markets. Today, the Netherlands produces more than 4.5 billion tulip bulbs annually on approximately 12,000 hectares of land. To put that in perspective, if you laid all those bulbs in a single line, they would circle the earth more than twice. The economic impact is staggering. The Dutch ornamental horticulture sector generates over 9 billion euros in annual revenue and directly employs more than 60,000 people. Flower and bulb exports account for a significant portion of Dutch agricultural exports, with the United States representing one of the largest markets, consuming hundreds of millions of bulbs and cut flowers every year. International comparisons reveal just how dominant Dutch flower farming has become. The Netherlands produces more tulips than the rest of the world combined, while countries like the United States, France, and Japan have their own tulip industries. They collectively account for less than 15% of global production. What makes this even more remarkable is that the Netherlands is one of the smallest countries in Europe, with a total land area roughly the size of Maryland. This tiny nation has transformed limited space into agricultural productivity that rivals countries hundreds of times larger through relentless innovation and technological advancement. One shocking fact that surprises even agriculture professionals is that much of the land used for Dutch flower farming did not exist a century ago. Significant portions of the Netherlands have been reclaimed from the sea through massive engineering projects, creating polders, areas of land protected by dikes and kept dry through constant pumping. The famous Noordoostpolder, where much tulip cultivation occurs, was underwater until the 1940s. Dutch growers literally created their own farmland, then optimized every square meter for maximum production through techniques that are now studied by agricultural innovators worldwide, including forward-thinking American farmers looking to maximize greenhouse production. The initial stage of tulip production begins not with planting but with breeding programs that can span 15 to 20 years before a new variety reaches commercial markets. Dutch breeding companies employ teams of geneticists, horticulturists, and market analysts who work together identifying desirable traits and developing varieties that meet evolving consumer preferences. Breeders seek flowers with strong stems that resist breaking during handling, vibrant colors that remain stable as flowers mature, long vase life that satisfies retailers and consumers, and disease resistance that reduces chemical inputs and crop losses. The breeding process starts with controlled pollination, where breeders manually transfer pollen from selected parent plants to flowers chosen for specific characteristics. Each pollinated flower produces a seed capsule containing dozens of individual seeds. These seeds are collected, cataloged with detailed information about their parentage, and planted in test fields. From seed to first flower takes 3 to 5 years, and breeders must wait to see which genetic combinations produced desirable results. Promising seedlings enter multi-year evaluation trials, where they grow alongside thousands of other candidates. Breeders assess each plant for vigor, flower quality, bulb production, and disease resistance. Out of 10,000 original seedlings, perhaps only 1 or 2 will eventually achieve commercial release. The survivors receive official registration with the Royal General Bulb Growers Association, gaining names and trademark protection. This rigorous selection process ensures that only truly exceptional varieties reach professional growers and eventually consumers. Bulb multiplication takes additional years before sufficient quantities exist for commercial production. A single mother bulb produces 2 to 4 daughter bulbs annually, depending on variety and growing conditions. Building inventory from a handful of bulbs to the millions needed for large-scale production requires patience and careful planning. Breeding companies must project market demand years in advance, deciding how many resources to invest in multiplying each new variety. This long timeline means that varieties available in stores today represent breeding decisions made a decade or more in the past. Environmental requirements for tulip cultivation are exacting, and modern Dutch greenhouses provide unprecedented control over every variable affecting plant growth. Traditional field cultivation remains important for bulb production, but increasingly, cut flower production occurs in sophisticated greenhouse facilities that use automated systems to create perfect growing conditions regardless of outside weather. These structures represent some of the most technologically advanced agricultural facilities anywhere on Earth, incorporating innovations that American greenhouse operators are rapidly adopting. Temperature control begins with computer systems that monitor conditions throughout the greenhouse using networks of sensors reporting data every few seconds. Tulips require cool temperatures during initial root development, typically between 45 and 55 degrees Fahrenheit. Heating systems using natural gas boilers or geothermal energy maintain minimum temperatures during cold periods, while ventilation systems open roof vents and sidewalls to prevent overheating on sunny days. The computers constantly adjust heating and cooling to maintain optimal conditions while minimizing energy consumption, a critical consideration given European energy costs. Lighting systems supplement natural daylight during short winter days, providing the additional photons plants need for robust growth and flower development. Modern facilities use LED grow lights that produce specific wavelengths matched to plant photosynthetic requirements, while using 70% less electricity than older high-pressure sodium lamps. The lights are arranged on movable frames that automatically adjust height as plants grow, maintaining consistent light intensity at the canopy level. Computerized controllers dim lights or turn them off entirely when adequate natural light is available, reducing costs and environmental impact. Water and nutrient delivery occurs through precision irrigation systems that would impress even the most tech-savvy American farmers. Dutch growers pioneered closed-loop hydroponic systems where plants grow in inert substrates like perlite or rock wool rather than soil. Nutrient solutions containing exact concentrations of nitrogen, phosphorus, potassium, and micronutrients are delivered directly to plant roots through drip emitters controlled by computer programs. Sensors measure the electrical conductivity and pH of the solution before and after it passes through the growing medium, allowing real-time adjustments to maintain optimal fertility. What makes these systems truly remarkable is that any solution not absorbed by plants is collected, tested, adjusted, and recirculated rather than being discharged as waste. This closed-loop approach means virtually zero nutrient runoff into groundwater or surface waters. A stark contrast to traditional field agriculture where fertilizer losses can be substantial. Water use efficiency is equally impressive. Modern Dutch greenhouses use 90% less water per flower produced compared to field cultivation, an achievement that has tremendous relevance for American agriculture as water scarcity intensifies across western states. Carbon dioxide enrichment provides another layer of environmental optimization. Plants use carbon dioxide during photosynthesis to build sugars and starches that fuel growth. Ambient air contains approximately 400 parts per million of carbon dioxide, but research has shown that many crops grow faster and more efficiently at concentrations between 800 and 1200 parts per million. Dutch greenhouses capture carbon dioxide from heating system exhaust or purchase it in liquid form, then release controlled amounts into the growing environment. Sensors throughout the facility monitor concentrations continuously, and computers adjust release rates to maintain target levels. This enrichment can increase growth rates by 20 to 30%, while improving stem strength and flower quality. Early care during the establishment phase requires meticulous attention even in highly automated facilities. Bulbs arrive at greenhouse operations after spending months in temperature-controlled storage that prepares them for forcing, the process of bringing them into bloom outside their natural flowering period. Robotic planting systems developed by Dutch engineering companies can process thousands of bulbs per hour, placing each one precisely into growing trays or benches at optimal spacing and depth. Mechanical arms equipped with vision systems identify the top and bottom of each bulb, orienting them correctly for planting without any human intervention. As shoots emerge from bulbs and begin growing toward the lights above, automated monitoring systems track development using cameras positioned throughout the greenhouse. Image analysis software measures plant height, leaf color, and growth rates, alerting growers to any areas showing signs of stress, disease, or nutrient deficiency. This allows intervention before problems spread, maintaining uniform crop quality across thousands of square meters of production space. Some advanced facilities use thermal imaging cameras that detect temperature differences, indicating irrigation problems or disease development before symptoms become visible to the naked eye. Mobile robots patrol greenhouse aisles on fixed tracks or autonomous navigation systems, performing tasks that once required armies of workers. These machines can apply targeted sprays for pest and disease control, removing the need for broadcast applications that waste materials and create unnecessary environmental exposure. Other robots scout for problems, using artificial intelligence to identify diseased plants that need removal before pathogens spread to healthy neighbors. The machines work around the clock without fatigue, providing surveillance and intervention capabilities impossible with human labor alone. The harvesting stage represents a critical transition where flowers move from the protected growing environment into the supply chain that will deliver them to markets worldwide. Timing is absolutely essential. Tulips must be cut at precisely the right developmental stage to ensure they open properly after reaching consumers while surviving several days or even weeks in cold storage and transport. Cut too early, and flowers may fail to open. Cut too late, and they mature too quickly, reducing vase life and market value. Dutch growers harvest tulips in the tight bud stage when color is just beginning to show but petals remain tightly closed around reproductive structures. At this stage, flowers can withstand the handling and temperature fluctuations inherent in modern distribution systems. Professional harvesters, whether human workers or increasingly robotic systems, cut stems at a uniform length that meets market specifications. For most markets, stems are cut between 14 and 16 inches long, though some specialty markets prefer shorter or longer stems. Manual harvesting still dominates in many operations despite advancing automation. Skilled workers move through greenhouse rows with incredible speed, evaluating each flower in a fraction of a second, and cutting only those that meet quality standards. The cut stems are immediately placed in buckets containing water or preservative solutions that prevent wilting and extend shelf life. Workers can harvest over 1,000 stems per hour, but labor costs and availability challenges are driving rapid adoption of mechanical alternatives. Robotic harvesting systems represent the cutting edge of agricultural automation, with applications extending far beyond flower production. These machines use advanced computer vision systems with multiple cameras and artificial intelligence algorithms trained on millions of flower images. The system identifies flowers ready for harvest based on color, size, and developmental stage, then calculates the optimal cutting point on the stem. Robotic arms equipped with sharp blades make clean cuts without damaging adjacent plants, matching or exceeding the speed and precision of human harvesters. Transportation from greenhouse growing areas to processing facilities must occur quickly to maintain quality. Most Dutch operations have packing and sorting facilities directly adjacent to or even integrated within greenhouse structures, minimizing the time flowers spend out of water and climate-controlled environments. Flowers move through facilities on conveyor belts or in wheeled carts, never remaining at ambient temperatures for more than a few minutes. This attention to the cold chain, maintaining consistently cool temperatures from harvest through retail sale, is what allows Dutch flowers to arrive at destinations thousands of miles away in pristine condition. Processing facilities transform freshly cut flowers into the uniform, packaged products that retailers and wholesalers demand. The first step involves grading and sorting, processes where flowers are separated into categories based on stem length, flower size, and overall quality. Until recently, this required teams of workers manually evaluating each stem. Today, the most advanced facilities use machine vision systems and robotic sorting that process up to 30,000 stems per hour with remarkable accuracy. Flowers enter the automated systems on high-speed conveyor belts, moving at speeds that blur individual stems into a continuous stream of color. Multiple cameras positioned above, below, and beside the conveyor capture dozens of images of each stem from different angles. Image processing software analyzes these pictures in milliseconds, measuring stem length and straightness, flower size and color, and checking for defects like damaged petals or disease symptoms. Based on these measurements, the system assigns each flower to a quality grade. Mechanical diverters, controlled by the computer system, physically separate stems into different lanes based on their assigned grades. High-speed pneumatic pushers, or robotic fingers, gently redirect each stem at precisely the right moment, sending premium-grade flowers to one processing line, standard grade to another, and culls to a third line for disposal or alternative uses. The entire evaluation and sorting process occurs so rapidly that a single flower spends less than 1 second moving from the entrance conveyor to its assigned grade category. Quality control extends beyond simple physical measurements. Some facilities use spectrometers that analyze the precise color of each flower, ensuring consistency within batches and matching customer specifications. Others employ near-infrared sensors that can detect internal defects or disease organisms invisible to cameras operating in visible wavelengths. These quality inspection systems catch problems that would otherwise reach customers, protecting brand reputation and maintaining the premium pricing that high-quality Dutch flowers command in global markets. Washing and cleaning are essential steps, ensuring flowers arrive at destinations free from soil, insects, and chemical residues. Automated washing systems spray flowers with clean water or mild sanitizing solutions as they move through processing lines. Rotating brushes gently agitate stems and foliage, dislodging debris without damaging delicate tissues. After washing, forced air dryers remove surface moisture that could promote fungal growth during storage and shipping. The entire cleaning process takes less than a minute per stem, but dramatically improves both appearance and shelf life. Stem trimming occurs after sorting and cleaning, bringing all flowers within each bundle to precisely uniform lengths that meet retail standards. Automated cutting stations use laser measurements to identify the base of each stem. Then pneumatic guillotines make perfectly square cuts at the specified length. These clean, uniform cuts not only look professional but also maximize water uptake when flowers are placed in vases, directly impacting vase life and customer satisfaction. Bunching and bundling transform individual stems into the presentation formats that retailers and consumers recognize. Automated bundling machines gather predetermined numbers of stems, typically 10 or 25 depending on market preferences, and wrap them together with rubber bands or decorative sleeves. Robotic arms position flowers so that blooms align attractively and stems are parallel, creating bundles that look hand-arranged despite being assembled by machines, operating at speeds no human could match. Packaging systems protect flowers during the journey from Dutch processing facilities to retail locations around the world. Most bundles are placed in long cardboard boxes specifically designed for cut flower transport. These boxes have reinforced corners and ventilation holes that allow air circulation while protecting delicate flowers from crushing. Automated packaging lines fold flat boxes into shape, insert flowers, add protective tissue paper or bubble wrap as needed, seal boxes with tape, and stack them on pallets ready for shipping. Modern lines process over 500 boxes per hour with minimal human involvement. Labeling provides traceability and marketing information required by modern supply chains. Each box receives labels identifying the grower, variety name, stem count, quality grade, and harvest date. Barcodes, or QR codes, link to databases containing detailed production information, allowing retailers and even consumers to trace flowers back to specific greenhouse blocks and harvest days. This transparency builds trust and provides accountability throughout the supply chain, reflecting food safety principles that have become standard in produce industries and are now being adopted for ornamental crops. Cold storage represents the critical link that allows Dutch flowers to reach distant markets in salable condition. Processing facilities contain large refrigerated rooms maintained at temperatures between 32 and 36 degrees Fahrenheit. At these cool temperatures, flowers enter a state of suspended animation where metabolic processes slow dramatically. Cell respiration, the process that consumes stored sugars and eventually leads to senescence and death, proceeds 5 to 10 times slower at refrigeration temperatures compared to room temperature. This cooling effectively stops the biological clock, allowing flowers to remain in perfect condition for weeks rather than days. Temperature control within storage facilities requires sophisticated refrigeration systems and careful management. Commercial coolers use industrial refrigeration units that can maintain precise temperatures, despite frequent door openings and the heat load from freshly harvested flowers entering at warmer temperatures. Monitoring systems track temperatures throughout storage spaces, alerting managers if any areas drift outside acceptable ranges. This vigilance prevents warm spots that could cause premature aging or cold spots that might cause freezing damage. Humidity management within cold storage is equally important. Air that is too dry causes flowers to lose moisture through transpiration, leading to wilting and reduced vase life. Air that is too humid promotes mold and bacterial growth that can destroy entire shipments. Modern storage facilities maintain relative humidity between 85 and 95%, the range that minimizes water loss while preventing disease development. Automated humidification systems add moisture when humidity drops too low, while dehumidifiers remove excess moisture when levels climb too high. Distribution channels connect Dutch production with global markets through one of the world's most efficient logistics networks. The centerpiece is Royal Flora Holland, the massive flower auction cooperative that operates facilities processing over 12 billion flowers annually. At the main location in Aalsmeer near Amsterdam, Flowers arrive throughout the night from growers across the Netherlands. Automated systems sort incoming shipments, prepare them for auction, and transport them through cavernous halls on miles of conveyor belts. The auction itself operates using a unique descending price clock system, where prices start high and drop rapidly until a buyer presses a button to purchase a lot. This Dutch auction method processes over 100,000 transactions daily, with individual lots of flowers selling in just seconds. Buyers include wholesalers, retailers, and exporters purchasing flowers that will be in stores from Paris to Tokyo within 48 hours. The speed and efficiency of this system set global price benchmarks and demonstrate how agricultural product distribution can operate with manufacturing-level precision. For international markets, particularly the United States, flowers move from auction facilities to Amsterdam's Schiphol airport, one of Europe's busiest air cargo hubs. Refrigerated trucks transport flowers in climate-controlled containers, maintaining cold chain integrity throughout the journey. At the airport, specialized air cargo handlers with expertise in perishable goods load flowers onto passenger and dedicated cargo flights. Flight times from Amsterdam to major American cities range from 8 to 10 hours, and flowers often move from Dutch greenhouse to American wholesaler within 24 to 36 hours of harvest. American florists, grocery stores, and mass-market retailers purchase Dutch tulips through established importing networks. Specialized flower importers maintain relationships with Dutch growers and auction buyers, arranging for container shipments during peak seasons and ensuring consistent supply year-round. These importers operate their own distribution centers with cold storage facilities and delivery fleets that serve retailers across specific regions. The efficiency of this distribution system means that consumers in California or New York can purchase tulips that may have been growing in a Dutch greenhouse just 2 or 3 days earlier. Byproducts from tulip production find valuable uses rather than going to waste. Bulbs that have been forced for cut flower production exhaust their stored energy reserves and are generally unsuitable for reflowering at commercial quality. However, these spent bulbs contain valuable organic matter and nutrients. Dutch growers compost them, creating soil amendments that improve structure and fertility in field production areas. Some operations also pelletize dried bulb waste, creating biomass fuel that can be burned in heating systems, completing a closed loop where waste from one production cycle powers the next. Foliage and stems trimmed during processing similarly become feedstock for composting operations or anaerobic digesters that produce biogas. These digesters break down organic matter in the absence of oxygen, generating methane-rich gas that can fuel electricity generators or heat boilers. The remaining digestate after biogas extraction is a nutrient-rich slurry that serves as organic fertilizer. This waste-to-energy approach reduces fossil fuel consumption while managing organic waste in environmentally responsible ways that agricultural operations worldwide are studying and implementing. Culinary applications for tulips might surprise viewers unfamiliar with edible flower traditions. While modern commercial tulip varieties are grown exclusively for ornamental purposes, tulips are technically edible and historically were consumed during times of scarcity. The most famous example occurred during the Dutch hunger winter of 1944 and 1945, when tulip bulbs became an emergency food source for starving populations. The bulbs can be ground into flour or sliced and cooked, though they are quite bitter and require special preparation to become palatable. Today, some specialty farms grow specific tulip varieties for the edible flower market, where petals add color and mild flavor to salads, desserts, and beverages. These culinary tulips must be grown without synthetic pesticides or chemicals, following organic protocols that ensure food safety. The petals have a slightly sweet, sometimes cucumber-like flavor that complements spring salads and can be candied for decorating cakes and pastries. This niche market remains tiny compared to ornamental production, but demonstrates the versatility of these remarkable flowers. Nutritional value of edible tulip petals is modest but not insignificant. Fresh petals contain small amounts of vitamin C, beta-carotene, and various antioxidant compounds that contribute to human health. However, Because quantities consumed are typically very small, tulips should be viewed as garnishes that add visual appeal rather than as significant nutrient sources. The real nutritional story of Dutch flower farming relates not to the flowers themselves, but to the agricultural innovations developed in this industry that have applications for food crop production. Environmental impact and sustainability have become central concerns for Dutch growers who recognize that long-term success requires environmental stewardship. The flower industry has faced criticism for chemical pesticide use, energy consumption, and water pollution. In response, the sector has pioneered integrated pest management approaches that dramatically reduce chemical inputs. Beneficial insects and mites that prey on common flower pests are released throughout greenhouses, providing biological control that works alongside targeted chemical applications only when absolutely necessary. Some facilities have reduced pesticide use by over 70% compared to practices from 2 decades ago. Energy efficiency improvements have been equally dramatic. Modern Dutch greenhouses produce 4 to 5 times more flowers per unit of energy compared to facilities from the 1980s. Advances include ultra-transparent glass coatings that maximize light transmission, insulated screens that reduce nighttime heat loss, LED lighting that converts electricity to useful photons far more efficiently than older technologies, and combined heat and power systems that simultaneously generate electricity and capture waste heat for greenhouse heating. Some facilities achieve near energy-neutral operation, producing almost as much energy as they consume through solar panels and biogas generators. Water conservation through closed-loop hydroponic systems eliminates the groundwater pollution that plagued earlier generations of intensive agriculture. By capturing and recycling all irrigation water, modern facilities prevent nutrient runoff that once contaminated surface waters and caused algae blooms in sensitive ecosystems. Some greenhouse operations harvest rainwater from roof surfaces, storing it in underground reservoirs for irrigation use. This reduces demand on municipal water systems and aquifers, demonstrating that intensive agriculture can coexist with environmental protection when growers embrace innovative practices. Sustainability certification programs provide third-party verification of environmental and social responsibility. Many Dutch flower operations participate in programs like MPS ABC or Fair Flowers Fair Plants that audit production practices, chemical use, energy consumption, and labor conditions. Flowers meeting certification standards receive special labels that inform consumers about the environmental and ethical standards behind their purchases. American retailers increasingly demand certified flowers, creating market incentives for continuous improvement in sustainability performance. From the patient breeding programs that develop new varieties through 15-year journeys from seed to market-ready bulbs, through the computer-controlled greenhouse environments where every drop of water and degree of temperature is precisely managed, to the robotic harvesting systems and high-speed sorting facilities that process millions of stems with mechanical precision. Dutch tulip cultivation represents agricultural technology at its absolute pinnacle. The innovations pioneered in Netherlands greenhouses are now spreading worldwide as farmers and agricultural entrepreneurs recognize that the future of farming lies in combining biological understanding with digital technology and automation. The lessons from Dutch flower farming extend far beyond ornamental horticulture. The climate control systems, water recycling technologies, and automation strategies developed for tulips work equally well for vegetables, herbs, and even vertical farming systems being developed for urban environments. American farmers studying Dutch greenhouse methods are bringing these innovations home, building facilities that grow tomatoes in Texas, leafy greens in Kentucky, and strawberries in upstate New York, using techniques refined in the tulip greenhouses of Holland. This knowledge transfer represents agriculture at its best, where innovations developed in one place and contexts spread globally to benefit farmers, consumers, and the environment. Thank you for watching this journey through the high-tech world of Dutch tulip production, from bulb to bloom to bouquet. If you found this exploration of robotic greenhouse farming fascinating, please give this video a thumbs up and subscribe to AgriCraft for more deep dives into innovative agriculture from around the world and here in the United States. Leave a comment below telling us about your favorite flowers or agricultural technologies you would like us to cover next. Until next time, keep exploring the incredible innovations growing our future.